All right, so the next is integration. So integration is basically differentiation in reverse. So it's a reverse of differentiation, very easy to put. So we look at what uh, integration means and how it works. But let us first look at what do we mean by differentiation in reverse. So suppose we have this in y equals to x square and we differentiate it. So y is equals to x square. When I differentiate, I get dy by dx is equals to 2x. Right. Now, if I want to go back from here to here, right, from 2x to x square, what I need is integration. So integration reverses this process and we say that the integral of 2x is x square. So from x square, if I differentiate, I get 2x. And if I integrate, I get back x square. But you know, it's a little more complicated because there are lots of functions we can differentiate to give 2x. It's not that I always get back to the same function. So for example, if my original function here were x square plus 2, then by differentiating, I will get 2x. But by integrating, I'll not back x square plus 2. What will I get by integrating 2x?
X square.
X square, exactly. So if I differentiate x square, I get 2x. If I integrate x square plus 2, I get 2x. So a lot of all functions, so all the functions of the format x square plus k, when differentiated, will give me 2x. Okay, so differentiating any function of the format x square plus k is going to give me 2x. Simply for the fact that this constant, it gets cancelled when I differentiate. So when I integrate back, there is no way to get back this constant. What was this constant? Constant lost in differentiation and it cannot be generated back by integrating. Okay. So if I just give you the differentiated function, you cannot get the original function. Okay. You will get an image of the original function, at least the part which was not lost. The constant is lost in differentiation and that cannot be obtained. So what we say is that integration of 2x is not x square. What we say is integration of 2x is actually x square plus some constant c, which we assume was lost. Okay, so we say that the original function was something x square plus c. So the integration of 2x becomes x plus c. So 2x is the function that we are integrating and it's called the integrand. Now dx is the term with which with respect to which are integrating. So as we all know, this is right now what we are doing is just single variable. Everything that we are doing right now is single variable. We are going to change things up and move into multivariable. So suppose when I write integration of 2xy dx. So when I'm doing that, I will integrate with respect to x, which means that y will be assumed to be a constant. So integration of 2xy dx will basically be, since 2 and y are both assumed to be constant, this will now be treated as 2y integration of x dx. Right? So you can take this 2 and y outside and just integrate x dx. Okay, so and this snake side type structure is known as the integral sign. So this c is going to be constant of integration. So let's look at derivatives. So integration of x cube, x square plus 6, x cube plus 16, x cube plus x cube minus 21. All these differentiations are going to be 3x squared, right? Because we know that the differentiation of x to power n is basically n x to power n minus 1. So x cube's differentiation will be 3x squared, right? I think you have enabled some writing tool, so it happens by mistake. Anyway, so integration of x cube, x square, x cube plus 17, x cube minus 21, all these integrations are going to be 3x squared. So differentiation of all functions is going to be 3x squared. So when I write integration of 3x squared dx, it's going to be x cube plus c. Now this c, it could be anything. When c is 0, I get this function. When c is 17, I get this function. And when c is minus 21, I get this function. So for different values of this c, I can regenerate these functions. So these functions, they are all related in a way that all these functions have the same differentiation or same derivative. Then we have a table of integrals just to make your life easy. As you can see, it's going to be the reverse of integration, reverse of differentiation. So when I want to integrate x, I get half x squared c. So the way to verify it is differentiate this and check if you're getting this thing or not. Okay, if I differentiate half x squared plus c, it's d by dx is going to be half times x square ka differentiation is 2x, and c will die out because it's constant, so it's just going to be equal to x. Right? Uh, so these are your different integrations which might come in handy when you do the problems which are mentioned in these notes. With time, you will basically be able to deduce them or even remember them. So in general, I told you the differentiation of x to power n, that is d by dx of x to power n, is n x to power n minus 1. Now we are looking at integration x to power n. So integration of x to power n is x to power n plus 1 upon n plus 1 plus c. Okay. Again, simple to check. You differentiate this thing. When you differentiate this thing, you get 1 by n plus 1 is common. So I'll take it outside. Into differentiation of x to power n plus 1. So differentiation of x to power n plus 1 is going to be n plus 1 x to power n. So what you are left with is x to power n. So next example, find the indefinite integral of cos of phi x. Right? So cos of x, I want to integrate cos of phi x dx with respect to x. The word indefinite means that there are no limits to integration, to the integral. Now, what are limits to integral is something which we'll come to know in a bit. So when we do not have any limit, we call it indefinite. Uh, a definite integral looks like this. You put limits a and b on the integral itself. So we'll come to this section in a bit, but right now we are looking at indefinite integral where there are no such limits. So a and b are not present. So these are indefinite integrals. So integration of cos of phi x dx. So the formula is that integration of cos of kx dx is going to be sine kx kx by k plus. So in order to check this, just differentiate this one. So where I differentiate this 1 upon k is constant, so it comes outside, and just differentiation of sine kx. So differentiation of sine kx by chain rule is going to be cos of kx into differentiation of kx. So differentiation of kx is going to be k. So this is cos of kx. So integration of cos phi x is 1 by pi sine phi x. Let's see. So this year, I no Jam has asked a question on integration. So uh, of late they were not asking. Not many exams were asking questions from differentiation. Differentiation is important for us because it comes it is very important in calculating probabilities when we read statistics. So for a class of distributions which are continuous distributions, finding probability is basically going to be integration. All right. So this is interesting. Indefinite integral of 1 by x dx. So 1 by x dx. So whenever we want to integrate some function, integral f of x dx, I want to think of some function capital F of x such that the differentiation of this function should give me this function. So when I look at integration of 1 by x, I should think of some function whose differentiation will give me 1 by x. So I know from my differentiation table that differentiation of log x gives me 1 by x. Right? So this cannot be done in the way of x to power integration of x to power n. So integration of x to power n I saw was equal to x to power n plus 1 upon n plus 1. I cannot work in this manner because now what happens is because of 1 by x is basically x to power minus 1. So my n becomes minus 1. So this n plus 1 will become equal to 0. So that's why you cannot apply the formula of x to the power n. So 1 by x is special. Okay, 1 by x is special. So for 1 by x, that is x to the power minus 1, you know that the differentiation of log of x gives me 1 by x. So integration of 1 by x should be something like log of x. But the input of a log function has to be strictly positive. So that's why when I write this indefinite integral of 1 by x, what I do is I write log of mod x. Right? Because remember from our very first chapter when we were finding domains, right? The very first chapter, I told you that whenever you have log of some function f of x, this f of x needs to be greater than 0, strictly greater than 0. Log cannot take negatives or 0 as an input. Okay, so this mod x ensures that this input to the log is always positive. Okay, x anyway cannot be 0 because we are integrating 1 by x. For 1 by x to happen, this x cannot be 0 to begin with, but it can be negative. So when I put a modulus in front of it, I finally see that this integration, I finally see that this cannot be 0 and it cannot be negative. Right, so just remember this, that the integration of 1 by x is log modulus of x and not log x. Now integration of a constant, integration of 12 dx. So when you're integrating a constant, it's basically just integration of dx. Now integration of dx is integration of 1 times dx. So what function when differentiated gives us 1? So that is going to be x. So 12 into x plus. Okay, so 12x differentiation gives me 12. So the integration of 12x, 12 dx is going to be 12x plus. So then you can use the results here to solve a bunch of other problems. Now integration of e to power minus 2x dx. Right, so so for that use integration for e to power kx. So there are certain rules which are given in the table which I just showed you. So you can use those results like this table, this table. So it has the rules for e to power kf. So just substitute the value of k from here and but subsequently, we are going to see a lot of rules of integration, which will make it very easier for you to find these results. Just because you know differentiation, you can derive all these results. So there won't be any need to remember this entire table. The only condition is that you solve all the problems. So once you solve the problems, you remember the formula. You don't need to revise them or remember them. So some rules of integration. So integration of k times some function f of x. So when you are integrating k times f of x, you can take this constant outside and it just becomes integration of f of x. So integration of 11 times x square is just 11 times integration of x square. And I know that integration of x square is x cubed by 3 plus c. And then you take the 11 which you have already outside. So 11 times x cubed plus 3, x cubed by 3 plus c, which becomes 11 x cubed by 3 plus, this will become 11 x cubed by 3 plus 11c. Now, 11c is an unknown constant. So why do you want to write it as 11c? Why don't you write it as just some unknown constant k? The whole idea is you just want to put in an unknown constant there to represent the thing which is lost. Now you don't want you to write it as particular format. You just write it as some constants. So the way to do this would be just keep integrating, reach the last step, and add a constant in the last step. So that would be easier to do. So another way to do this would be integrate this. So 11 times x cubed by 3. So I don't add the constant in this step. Okay. So this becomes 11 x cubed by 3. This is the final answer which I want to report. And when I'm reporting the final answer, I just add a c just to add that constant which was lost in integration. Okay. Then there are a bunch of other things. So integration of minus 5 times cos x is just minus 5 times integration of cos x. I know from the table that integration of cos x is sin x plus c. So that takes care of everything. Now, if you have two functions f of x and g of x, or f of x minus g of x, then integration of f of x plus g of x is going to be integration of x plus integration g of x. A very nice property. This property helps us to integrate sums of functions. So when you have a sum of multiple functions, or let's say a polynomial functions. So a polynomial function is of the format a naught x, sorry, a naught plus a1x plus a2x square plus a3x cube plus so on till some an x to power n. So all functions of this format are called polynomial functions, Pn of x, polynomial of degree n in x. So these are called polynomial functions. So polynomial functions are simple powers of x added in some different ratios. It will have no sin x, cos x, log x, exponential x, no such noise. It will just have powers of. Okay. So when you have this function x cube plus sin x, okay, so I'm not saying that we use it only for polynomials. We can use it for any sums of functions. Whenever you see a sums of two different types of functions, you can use this property. So integration of x cube plus sin x is integration x cube plus integration sin x. Now individually know that this integration is this and integration of sin x is minus of cos x. So I'll do that. I'll not keep adding c1, c2 here. In the final step, I'll just add one constant c. So let's do this problem. Integration of 3t to power 4 plus root t with respect to dt. Okay, so integrate 3t to power 4 plus root t can be written as t to power half into dt. So the formula to use here would be that integration of x to power n is equals to x to power n plus 1 upon n plus 1 for n not equal to minus 1, and integration of 1 by x is equals to ln of mod x. So these are the two properties which we might need in order to do this particular integration. So what's it for? Sine from this formula that this can be written as integral 3 to power 4 dt plus integral t to power half dt. So Yuvakshi, what is integration of t to power 4 dt?
Sir, 3t raised to the power 5 upon 5.
And Kritika, what is integration t to power half?
Is 2 by 3 t to the power 3 by 2.
Very good. Plus c in the end. Okay, so this completes your result. So we just needed this property because there is no 1 by x format. So if I just know this property, that was sufficient here. Similarly, you can do these different problems which are given here. Yeah, hyperbolic sine and cosine functions you can ignore. These are basically inverses, sine and cos inverses. So these are trigonometric inverse functions. We are going to ignore inverse of trigonometric functions because it's not at all necessary. Now, I do suspect that maybe IIT JAM asks it. So we don't have enough proof on what IIT JAM is going to ask right now. It's mentioned in the syllabus, but they have not last year asked it. And it's been only 1 year for IIT JAM. So we don't know for sure how much they are going to get into trigonometry. Ideally, for an economics course, they do not need to get into too much of trigonometry. But being IIT, we don't know because IITians like a lot of maths. So my gut feeling is that we'll do some basic results of sine and cos, but we'll not get the inverses because inverses are very difficult to handle. This will not get into the inverse functions. We ignore the differentiation of inverse functions. We'll ignore the integration of inverse functions as well. Because it's a complete different maths altogether to do differentiation and integration. It's not at all necessary for economics. So that's why we are doing. Wherever you see this sine h of x, this is basically the inverse of sine x. This is inverse of cos x. So just ignore those problems. Okay, so these are a bunch of other exercises for you to do. So do them. When you have a function like this integration, okay, this will do now. Okay, so integration of x plus 3 whole square dx. So in order to do this, one way to do it would be through substitution, which we'll see later on. But right now, what we can do is without substitution, if you want to do is expand this bracket. So if I expand this bracket, x plus 3 whole square. So I know that a plus b whole square is a square plus 2ab plus b square. Right? 8 standard math. A plus b whole square. So by that formula, x plus 3 whole square is going to be x square plus 6x plus 9, right, into dx. And then you just integrate this thing. So integration of x square dx plus 6 times integration of x dx plus 9 times integration of dx. So that's how you can get it. So this will be x cubed by 3 plus x square by, sorry, 3x square plus 9x plus c. So this was the story of indefinite integral. Now let us look at a definite integral. All right. So suppose that when I integrate some function small f of x, I get some function capital F of x plus, where capital F of x is the function which when differentiated gives small f of x. So f prime of x, which is differentiation of capital F of x, will be small f of x. So for example, if your small f of x is function, your capital F of x will be this function, minus cos 3x by 3. So that is going to be capital F of x. So that differentiating this function gives me this function. So when I consider a definite integral, which is simply an indefinite integral, but with numbers written to upper and lower right of the integral sign. So the quantity integration f of x dx. What it basically means is capital F of b minus capital F of b. Okay, so if capital F was the integration of this function small f, then integration of small f from a to b is capital F of b minus capital F of b. So this is the simple meaning of a definite integral. The mathematical or other statistical importance of definite integral, which will become clear later on. But right now, an important doubt is that obviously I took capital F of x as a function whose differentiation gives me sine 3x. Okay. But this is not the only function which, when differentiated, gives 3x. I can take capital F of x as minus cos 3x by 3 plus 10. This function's differentiation will also give me sine 3x. So I can take different constants here. All these constants will give me the same small f of x sine 3x. But the beauty of a definite integral is that no matter what constant I assume here, this quantity remains unchanged. Okay, so to see this, consider that my f of x is actually minus cos 3x upon 3 plus some constant, some unknown constant. I don't know what this constant is. So f of b minus f of a will be equal to minus cos 3b upon 3 plus k minus cos 3a upon 3 plus k, which is basically minus cos 3b by 3 plus k plus cos 3a by 3 minus k. So the k cancels out, and what I'm left with is minus cos 3b by 3 minus cos 3a by 3, which would have been the same result had I taken this f of x as this one. So the constant cancels out in a definite integral. So the constant is redundant. So the value of the constant is completely redundant in a definite integral. So that's why definite integral may you take the simplest possible function to integrate. So don't clutter your calculations with this constant. So just assume the constant away. So take the simplest f of x, which when differentiated gives this sine 3x, which is the f of x which does not have any constant. So that will give you the simplest possible calculation because the constant is not going to play a role anyway. So how do I calculate a definite integral? So in order to calculate a definite integral, first I have to evaluate the integral. So suppose I want to integrate x square from 1 to 4. So integrating x, I know is 1 by 3 x cube plus c. But this c is not going to play any role, so I'm going to eliminate it anyway. And this is my function capital F of x. So integration 1 to 4 is just capital F of 4 minus capital F of 1. Now capital F of 4 for this function is 4 cube by 3 and capital F of 1 is 1 cube b. So 4 cube minus 1 cube by 3. So I know that 4 cube is 64. So 64 minus 1 by 3. So that's 63 by 3. So that's 20. So this is the way you write a definite integral. So integral f of x dx from a to b is capital F of x going from a to b. Okay, the sign is going from a to b. Okay, so when you write this, you are going from down to up, right? So it has to be f of b minus f of a, not the other way around. Because if you write it the other way around, you are going to get the negative. Negatives are very important here. So remember that you are going from down to up and not the other way around. So then there are a bunch of other problems, some related to sine functions, others simple polynomials. Now there are going to be some properties here. This is one key point. If you change the limits, you get the negative of this thing. Because this thing is f of b minus f of a, whereas this thing is negative of f of a minus f of b, which is basically f of b minus f of a. So if you want to interchange the limits, put a negative sign in front and then you can interchange the limits. All right, so suppose I have integration 1 to 2 x squared dx minus integration 2 to 1 plus integration 2 to 1 x squared dx. So what will this value be? Without calculating, without doing integrations, can you tell me this value? Just interchange the limits and see what happens.
So 0.
0, right? Because if I interchange the limits, this remains as it is plus minus integration of 1 to 2 x squared dx. So it's integration 1 to 2 x squared dx minus integration 1 to 2 x squared dx. So they cancel each other out and you get 0. So these are some exercises for you to do. So use the formula given in the table or otherwise, whatever you feel is comfortable for you. I just want the end result. Right? When you're doing this, the sine tables might come in handy. So you know sine tables, sine and for theta. So you saw sine of theta for theta pi by 3, pi by 6, pi by 3, pi by 2, and this pi by 4 also. Pi by 4, pi by 3, and pi by 2. Remember, pi is 180 degrees. So pi by 6 is basically 30 degrees. Pi by 4 is 45 degrees. This is 60 degrees, and this is 90 degrees. Sine sine table is also one more 0 for 0. This is theta, this is sine theta. For 0, sine theta is 0, 1 by 2, 1 by root 2, root 3 by 2, and 1. Now, you can find this in any math textbook sine table. And similarly, you can look at cosine table also. I have not added it into the text because I know all of you have done it before 10th. So I don't make it a point to add pre-10th level maths in my notes. So if you want, if at any point of time you get stuck at something like this, you can always Google it up. Maybe add it to your written notes that this is the sine table and this cosine table if you don't remember it. I remember it, and maybe if you don't, you can add it to your notes. Okay, so I always say maintain a formula sheet, and so a formula sheet could be you start writing on your notebook from the end, and just from this end of the notebook start writing all the formulae you find are difficult but I say are important to remember. So this is something which is important to remember: the sine table, the cosine table, and the tan table till 5. The reason it's important is till now nobody was asking this, but this year IIT Jam has asked it. Okay, has asked a question on science. Like I told you, inverse trigonometric still nobody has asked ever, so that's why we are still ignoring it. But sine they have asked once, so maybe it comes. Maybe you might get a question based on it. So you should not be stuck with a question just because you don't know the sine table, because this is something that we have studied in school. So you have no excuse absolutely to say कि okay मैंने revise नहीं किया था or whatever. So do add this, do know this table. It might be important for IT jam. Okay. Now, sometimes you have functions which have some integrals which can have infinity as its limit. Okay. So, for example, integration of e to power minus x dx. So, from the table that I have, I know that integration of e to power minus x dx is minus e to power minus x dx. A good way to check is differentiation of minus e to power minus x will be equal to e to power minus x. So integration of this has to be this. So integration of e to power minus x is minus e to power minus x. The limits are 0 to infinity. So this is just minus e to power minus infinity minus e to power 0. Okay. Now e to power minus infinity. So e to power minus infinity is just 1 by e to power infinity. Now remember that e is a value which is greater than 1. Okay, e is a value which is greater than 1, and that's why e to power negative infinity is going to be 0. Okay, so my final result is minus e to power minus infinity minus e to power 0. Now in this part, this is minus 1 by e to power infinity, right? E to power minus infinity can be written as 1 by e to power infinity. Now e is a value greater than 1, which implies e to power infinity will be equal to infinity. If instead of e here we would have had something like 0.5 or by 2, yeah, 0.5, then 0.5 to power infinity would have been 0. Okay, so if the number is greater than 1, then its power to infinity will become infinity. But if the number is smaller than 1, then its power to infinity would become 0. Luckily for us, we have e here, and since e is greater than 1, its power to infinity is infinity. So this becomes minus 1 by infinity, which is basically 0. So this thing becomes 0 minus negative of e to power 0. So e to power 0, anything to the power 0 is 1. Okay, anything to the power 0 is 1. So 0 minus minus 1 So that is going to be equal to 1. So sometimes limits could be infinity. In such situations, you might have to calculate limits also. Okay. Sometimes they are going to be 0. Right? So maybe a integral question actually devolves uh, into a limits question also in some situations, limits of functions. But we know how to handle it, so it's completely fine with us. So now integration of e to power minus x dx. So this is my e to power minus x, right? So at infinity, this thing goes to 0. So that's what they are saying, that at infinity, this thing goes to 0. So another way to do this would be to use limits. So instead of putting infinity here, what you put is some b value and limit b tending to infinity. Now this is obviously you are breaking the one-step thing into a two-step thing and elongating the process. It's not nearly really necessary, so that's why you can ignore it. You can put in. The correct way to do it would be, instead of putting infinity here, you put a value b, and then you say that this b is tending to infinity. So there are a bunch of other problems now. Hmm. Yeah, so there are a bunch of other problems which you can try for infinity and find their values. Now, one definite advantage of definite integrals is calculating area under the curve. So this is the question asked, which I was telling you, if this year IIT exam asked a question. So they basically asked area under the curve from, I think it was this year. Uh, so suppose you have a function f of x and you want to find the area under this curve contained between some limits a and x. Okay, some value x. So how do you find this area? All right. So let me draw a graph. So suppose this is my function f of x, and you want to find the area contained between these two limits. Let me draw another. So this is a better function f of x. So I want to find this area basically. I hope all of you get it. That I want to find this area. Okay, so how do I find this area? So one way to approximate this would be, so if I were to approximate it, what I can do is, I know that this value is some a, f of a, and this value is f of b. Okay, so I know that this is a and this is b. So this is f of a and this is f of b. Okay. So if I did not know any maths, any algebra, any integration, what I would do is I'll say, okay, this looks approximately like a rectangle with width of b minus a and height of between f of a and f of b. So I would say f of b plus f of a divided by. So I'd say take the medium height and integrate it. Okay. So this would be if I did not know any algebra. If I knew some algebra, what I'll do is I'll say, okay, a better way to do this would be, so if I went ahead with this calculation, what I'll actually calculate is this area. Now, obviously, there's some scope of error here. You see, this is not exactly this rectangular area which I just showed you is not exactly the area I was looking for. So there's going to be some scope of error. Another person would suggest that maybe what we can do is we can break it into two rectangles. Okay, this is a plus b by 2. This is the point a plus b by 2. A plus b by 2. So somebody else suggests that let's break it up into two rectangles and let's calculate the area of these two rectangles. The area of rectangle 1 could be, this is rectangle 1. So they say that this is rectangle 1 and this is my rectangle. So area of rectangle 1 is this base, which is a plus b by 2 minus a. This is the base. Into height, they assume it to be this value. So f of a plus b by plus the area of rectangle 2. So for area of rectangle 2, this is the base. So that is b minus a plus b by 2 into this is the height that they assume. So the height that assuming is f of b by 2. Sorry, f of b. So in this manner, if they proceed to calculate, the error is going to be this much. This is the error in calculation. This is the extra amount that you calculate the area as. So somebody comes along and says, okay, why are you breaking it into two pieces? Okay, let me keep this here. Instead, let us break it into four pieces. Somebody else comes along and says, let's break it up into four pieces. So he says that let's break it up into rectangle 1, then rectangle 2, then rectangle 3, and finally rectangle 4. So when we break it up into four pieces, the actual error is going to be just this much. So you can see the green error is definitely smaller than the yellow error. So the more rectangles you break it into, the more rectangles that you break your that you break your domain into, the less is going to be the error in calculation. So Leibniz was a mathematician who came along and he says that obviously if you keep increasing the number of divisions that you put on the x-axis, the closer you get to reality. So the actual area will be equal to summation of rectangles when you break it into infinite such rectangles. So when you break up this length of A to B into infinite rectangles, the width of each rectangle becomes 0. So what he says is that now what he does, what Leibniz did is, so he said, consider the same function f of x going from A to B. So he says, break it down into infinite rectangles, infinite small rectangles of width dx, dx and dz. Right, so now you have infinite rectangles of 0 width, which you want to find area on. So the area of this rectangle, so the height he says, you assume it to be the height at x. So at any point t here, at any point x plus t, the height is assumed to be equal to null value at x plus t. So the area of this rectangle is this area is basically the base is dx, sorry, the width is dx into the height f of x plus t. This is area of some nth rectangle, an. So you keep adding all these areas. So you just add up. So you sum up all these f of x plus t rectangles with dx width going from A to B. Now this is essentially what is given by integration f of x dx going from A to B. So this is the implication of your integration. Your integration is nothing but the area under the curve. Okay. So now when calculating the area, we just need to be careful about where the curve lies. The curve lying above x-axis. So if the curve completely lies above the x-axis, you can do a simple integration. All right. So the area between A to B under the curve f of x is just going to be given by this integration. So this is when the curve is completely above the x-axis. That is, f of x is always greater than 0, greater than equals to 0 for all x belonging to A to B. So if in all x in A to B domain, if f of x is not going below the x-axis, you can do this simple integration and get the result. So for example, integration of 1 by x dx. So this is 1 by x dx integration. So suppose you want to find the area under the curve 1 by x going from 1 to 4. So I know that this integration is log of mod x going from 1 to 4. So this is just log of 4 minus log of 1, right? And log of 1 is 0. So this is just log of 4. Right? So now that you know this, tell me what's going to be the area between 2 and 7. I'll just be back. There's somebody at the door. Yeah. So what's this value between 2 and 7?
So log of 3.5.
Very good. So this becomes log of 7 minus log of 2. So that is log of 7 by 2. So that is log of 3.5. Okay. So if you get a question like in which interval does this function have more area, between 1 and 4 or between 2 and 7, then obviously you know that it's going, this is log 3.5, this is log 4. So log 4 is larger. Log is a increasing function. 1 by x is a decreasing function, but log is an increasing function. So ln 4 is greater than ln 3.5, right? So this area is going to be larger than the area contained between 2 and 7. So you can get this indirect questions based on integration. Then you have this integration of sin x, which you can again do between 0 and 5. So I know that between 0 and 5, sin x is always positive. So sin x increases till pi by 2, which is basically 90 degrees, and it starts reducing. So sine curve is basically an oscillating curve. Right? So sine curve looks like an oscillating curve. It starts from 0. So this is your sine curve. Right? So this is your pi. This is 2 pi. This is 3 pi. This is 4 pi, and so on. On the other hand, cos curve is the same thing with some phase difference. Never good at drawing this. This becomes 0 here. Here it will achieve its minima. Here it will achieve 0. And here it will achieve its maxima. Then here it will again achieve 0. And here will achieve its minima, and so on it will go. Right? So it's similar, it looks just lagging behind the sine curve. The main thing is it starts from 1 at 0, at pi by 2 it is 0, at pi it is -1, and so on. Okay, so this is your cos of x, whereas this is your sine of x. So suppose you have a simple sin x and cos x curve. So now this is a more complicated thing. Now you are interested in finding this area. Okay, so the area between cos x and sin x curve between 0 and pi by 4. So suppose I am interested in this. So calculating such areas is going to be the kind of questions you can expect in exam, if at all you get an integration question. So this curve at any point x, this length is basically cos x minus sin x. Right? X is larger, sin x is smaller. So I can calculate it as just cos of x minus sin of x dx. Okay, this is the height. So remember rectangles. So I want to add up all these smaller rectangles. So when I am adding these small rectangles, the height is cos x minus sin x, and the width is dx. You just integrate it from 0 to pi by. So when I do this integration, I'm going to get. Now, find what this value is going to be. That's your part 1. Part 2 is what is going this area plus this area. So that is your second. So find the red shaded area. So that's your second question. So give me these two questions. The answers to these two questions. You have 2 minutes to do it. Yeah. So yeah, so this part, the first region, this black shaded region, So this is integration cos x minus sin x going from 0 to pi by 4. So I know that integration of cos x is sin x and integration of negative sin x is cos x going from 0 to pi by 4. Right? You can differentiate this. When you differentiate sin x plus cos x, you are going to get cos x minus sin x. So yeah, I know that this is. So this is basically sin x going from 0 to pi by 4 minus so plus cos x going from cos x going from 0 to pi by 4. Okay. So sin x from 0 to pi by 4 is sin pi by 4 is root 2. Sorry, 1 by root 2 sin x plus cos x. Let me write it here. Sin x plus cos x going from 0 to pi by 4. So that is sine of pi by 4 minus sine of 0 plus cos of pi by 4 minus cos of 0. Right? So sine pi by 4 minus sine 0. So this is 1 by root 2 minus 0 plus cos pi by 4 is also 1 by root 2. But this thing is minus of 1. Cos 0 is 1. Cos cosine table is different from sine table. So this is basically root 2 minus 1. Right? So you can write this as 2 by root 2 minus 1, but 2 by root 2 just becomes root 2 minus 1. So this is root 2. So this area is root 2 minus 1, which is positive because root 2 is 1.414, so it had to be positive. Now, when I'm solving this area, one mistake which a lot of people do is, since you're going from 0 to pi by 2 here, what they do is they put limits as 0 to pi by 2. Now, when I do that, I'll get these things. Now, sine pi by 2 is 1, cos pi by 2 is 0 minus 1. So 1 minus 0, 0 minus 1. So that would become 1 minus 1. So that is 0. So you'll get the result if you just make this limit as twice, you'll get this result as 0. The reason that you get this as 0 is that when you're taking the area, you're taking the height here. The height here is cos minus sine, whereas the height in this region is sine minus cos. Because now the sine curve is above the cos curve. Right? The sine curve is more than the cos curve. So when you continue to use the same formulation, you are taking the negative of height. So that's why what you get is the negative of area. So whatever area you got here as A1, the area that you get here by continuing to use the same formulation will be minus of A1, and these two areas they cancel. So what I need to do now is either one idea is definitely to just double the area, which is correct here because of symmetry. So if you can set this thing is going symmetrically, you have already calculated area E1, which is root 2 minus 1. So you can just twice it to get the total area. Another way to do it, a more correct way of doing it when you're not sure about symmetry is just integration 0 to pi by 4 cos x minus sin x dx plus integral pi by 4 to pi by 2 minus of cos x minus sin x dx. So I'm adding a negative sign here. The reason I'm adding a negative sign here is I'm removing the negative which is coming from the height being negative. Or otherwise, what I can write here is sin x minus cos x, because I know that in pi by 4 to pi by 2 regime in this region, the sine curve is larger than the cos curve. So I can use height as sine minus cos instead of cos minus sine. So when I do that, I know that this area is root 2 minus 1. So this area will be cos x minus sine x. No, negative of cos x minus sine x. Sine x minus cos x. Going from pi by 4 to pi by 2. And when you expand this, this will also come out as root 2 minus 1. So this root 2 minus 1 plus this root 2 minus 1, they both add up to be twice of root 2 minus 1. Okay. So then there are a bunch of other problems related to this. So parts which lie below the curve x-axis. So now this is the case when you have parts of a curve lying below the x-axis. Suppose you want to find the area bounded area here, which is absolutely below the x-axis for this function f of x. So I know that if I just do integral f of x dx going from 1 to 2, what I am going to get is minus a. So in order to get this area a, I need to put a negative in front of this. So when you're calculating area under the curve, just write negative a.
Or so the other way can it be like taking the mod of the area, because the area cannot be negative in any case?
Okay, I'll tell you what the problem is. Taking mod of area, first you need to find the area, right? The example that I am going to give now will make this clear why mod will not work. So suppose I have this function. Which looks like this, going from A to. I want to find this region, this area, this entire area. Suppose this function is f of x, and this point is, let's say, C. So what you're suggesting is mod integration of f of x going from A to B, is it?
No, sir. Taking the individual mods,
Mod of what?
mod of area from A to C and then from C to B.
Correct. That's fine. That's fine. If you do that, then there is no problem. Okay. So if you do that, you are adding this area A1 and this area A2. That's okay. That will work. This will not work. By the way, this will not work because what happens in this case is this area and this area A1 and A2, they are bound to cancel each other out. What you will get is strictly something which is lower in magnitude than these two areas. So suppose A1 is this area and A2 is this area in magnitude. This result will come out to be A1 minus A2. What you need is A1 plus A2. Now, in order to find that, you need to know this. If you are unsure about C, this technique cannot work. So this C where the function becomes positive and where it becomes negative is absolutely important in finding this area. So now this A1, it will basically be integral f of x dx going from A to C. And this A2, this will be integral f of x dx going from C to B connect. Or instead, you can write it as B to C. because I know that integration from B to C is negative of integration from C to B. So you can just reverse the limits. And this final area is going to be integral A to C f of x dx plus integral B to C f of x dx. Okay. So you have to be careful about where is it positive and where is it negative. So suppose I give you this example. So the example is a function f of x has defined on A to B has a unique root, that is a single point where it becomes 0 at C, which is somewhere between A to. So it has some unique midpoint. So area between the function f of x and x axis can be option A, integral A to B f of x dx plus integral A to C f of x dx plus integral C to B f of x dx. Option B, integral A to C f of x dx plus integral B to C f of x dx. Option C, integral C to A f of x dx plus integral C to B f of x dx. And option D is integral C to A f of x dx plus integral, what is that, C to A में B to C हो गया, so C to B, so B to C f of x. So which of these can be true? Can be. More than one can be correct. What? Not only one option correct. Multiple options can be correct. So which one or which multiple of these options do you think can be correct? It has a unique root at 0. Take your time. This is probably one of the more difficult problems. Think about situations where you might get this result. Can you, in your head, construct a function f of x on A to B which satisfies this unique root property for which one or more of this? So just look at option A and think of some function f of x for which the total area would be given by this.
Yes, sir, the first option.
Can you give me an example of a function where it could be true? You
So
did
the
not.
case
Yeah.
which you just gave, the previous example.
Okay, here I told you that the area is going to be A to C plus B to C. Here I have A to C plus C to B. Okay, so in this case, this would represent the area when f of x is positive in A to C and it is positive in C to B. So if this is, let's say, my A, this is, let's say, my B, and this is, let's say, my C. A function which looks like this, which has a unique root at C, will give me area which is going to be given by this integration. Because this area is, in this area, function is positive, and this area also it is positive. So this is correct for a function of this format. It could be something else also. It could look like this. Okay, it need not be just straight line. It could be anything which is all positive, or it could be looking like this. I don't care what it looks like as long as it is positive everywhere apart from 0. So in that case, this will give me the correct area. Okay. Now this B is basically writing it in this manner. C to B minus f of x. So it should be positive here and it should be negative here. So I can have a function on A to B which is positive here and negative here. Right? So here the area is going to be given by this. So B is also. So similar constructions tell me C and D can be correct. I've given you the biggest possible hint. So now it should be B here.
So the other way around for the B part, like it's negative in A to C and then positive in C to B.
Very good. So this would be true if you have a curve which looks like this. So negative here and negative here. So basically here C to B is going in the right direction. A to C is reverse of C to A. So what I can write this as A to C negative f of x. So if f of x is negative from A to C and positive from C to B, so then such a curve would be its area under the area between the curve and x-axis will be given by this formula. So this can also be correct. And coming to D part, now it should be clear, right? That this is also correct. Here I have reversed both of them, so it will be reverse of this particular option. So it would be a curve like this. So when it is negative on both sides, so it's negative everywhere. So in that case, I will have to reverse both of them and then put negative here. So it should be negative in both the regions. So this curve can, such a curve which is always below the negative, below the x-axis, its area will be given by this result. So for a curve which looks like this, all these four can give me the integration. All right, so this is area under the curve. Now, okay, integration by parts. Important technique. So in integration by parts, sometimes I have a multiple of two functions and I want to integrate it. All right, by the way, I'm rushing a bit here. There would be a few problems which you have to do. So these different examples which they are given. So do that and uh, do this function also, sketching the graph and stuff. Okay, indifferent integration. So integration by parts. So in integration by parts, you have a multiple of two functions which you want to integrate. So in this case, I am going to use the isolate technique. The isolate technique helps me fix the hierarchy. So when using the integration by parts mechanism, I want to fix the hierarchy of the two functions. So let's say this is function 1 and this is function 2. Okay, or this is function 2 and this is function 1. So how do I fix that hierarchy? So the hierarchy is important here because integration by parts is not a symmetric rule. You'll see what that thing is. But first, I want to describe what is isolate. Isolate is hierarchical. A function which comes earlier in this nomenclature is given a better rank. Better rank being a lower value. So I is inverse trigonometric. I is inverse trigonometric, which we don't have in our syllabus. L is logarithmic. A is algebraic. T is trigonometric. And E is exponential. So when you look at this function, e to power 2x is exponential and sine 3x is trigonometric. So trigonometrics is bit higher on the hierarchy. So I should nomenclate this as function 1 and this is function. Okay. So how does this work now? Now that I have my first function and the second function. So the integration by parts says that function 1 into function 2 ka integration is first function integral of second minus integration of differentiation of first function into integral of second. Okay, so first function into integral of second plus integral of differentiation of first function multiplied by integral of second. Okay, absolutely important to remember this. It has been asked in the past 5 years by, I guess, TKC. So if something is asked in the past 5 years, I put it as something important. If it is not asked at all in the past 5 years by any of these exams, I tell you, okay, this you can ignore. Because if it's asked, it can be asked again. It has been asked multiple times in the past 15 years, including at least once in the past 5 years. So that's why I say that remembering this is very important. So this is one of the formula which should go into your formula sheet, integration by parts. So once you know this, after that, it becomes very easy to do this integration thing. All right, so first function integral of second. So integration of e to power 2x sine 3x dx. So let me do that. What was it? Integration of e to power 2x sine of 3x dx. So as I told you, this is going to be my first function. This is going to be my second function according to isolate regime. So first function, which is sine 3x into integral of second. So integral of second is e to power 2x dx. Minus, sorry, plus integral of differentiation of first function. So that's cos of 3x. So 3 cos 3x. Differentiation of sine 3x is 3 cos 3x. Okay, so integration of differentiation of first function into integral of second. Now integration of e to power 2x is e to power 2x by 2. So this is sine 3x into e to power 2x by 2 plus integration of 3 cos 3x into e to power 2x by 2. Now again, I'm stuck with the isolate thing here. So this 3 by 2 times integration of cos of 3x into e to power 2x. So I'll again apply isolate. So according to isolate, again, this should be my function 1, this should be my function. So let's just focus on this integration. So this integration, again, first function, oh no, sorry, yeah, this should be my first function and this should be my second function. So first function into integral of second plus integral of differentiation of first function, so minus sine 3x by 3 into integral of second. So integral of second is e to power x by 2. So differentiation of first, so minus 3 sine x. First function into integral of second minus integral of differentiation of first function into integral of second. Right. So this is cos 3x into e to power 2x by 2 minus integration of 3 by 2, I'm taking outside, sine 3x e to power 2x dx. Now notice that these two things are the same. So what I can do is I can call this integration as I. So basically what I have is I is equals to this thing, which is basically sine 3x into e to power 2x by 2 plus this thing. And then this thing becomes equal to this. So what I can write is that I is equal to sine 3x to e to power 2x by 2 plus 3 by 2 times. This red part became cos 3x into e to power 2x by 2 minus 3 by 2 times. This thing inside is basically I. So what I have is I is equals to 1 by 2 sine of 3x e to power 2x plus 3 by 4 times of cos of 3x into e to power 2x minus 9 by 4 times of I. Now this is I here, this is 9 by 4 I here, so I can take it on the other side, so I can get I plus 9 by 4 times of I, so that's basically just 13 by 4 times of I is equals to this. So I is equals to just 4 by 13 times of this thing. So sometimes this is the more difficult of integration by parts, where you have to do twice and use this result on integration. Sometimes it's going to be pretty straightforward. Sometimes integration by parts is going to be pretty straightforward. So there are going to be easier examples here. For example, integration of x sine x dx. So when I will do integration of x sine x dx, again use isolate. X is algebraic, so it goes here. Sin x is trigonometric, so it goes here. So this should be my first function, this is my second function. So first function into integral of second, so integration of sin x plus integral of differentiation of first term into integral of second. Integration of sin x is minus of cos x plus integration of minus of cos x. So that's going to be minus x cos x minus integration of cos x is just sin x. Minus x cos x minus sin x. When you differentiate this thing, you will get x sin x.
Excuse
So,
me, sir.
yeah,
So do we also have to write plus C, or is it
yeah,
redundant?
you can write it here. plus
Okay,
C.
sir.
If they ask you. So ideally, it's going to be, if a question like this comes, it should be in the subjective part. So if it comes the subjective part, then definitely. On the other hand, they might give you as a definite integral when it becomes unnecessary. So, like if a question like this comes, you get this entire thing and may write. So suppose it's a 10-mark question and I forget to write C, the examiner would at max deduct half a mark if he's in a bad mood. If he's in a good mood, he knows that you have done the more difficult thing, just you forgot the C. So it's like missing a full stop at the end of the sentence. Right? So unless you have a grammar Nazi who is checking, nobody's going to deduct marks for this in an economics exam. So yeah, so I won't worry too much about C. But if you put it, it's more correct. So you have these bunch of problems on integration by parts, which you need to work on. And then you have definite integral on integration by parts. Okay. So definite integral works in a similar manner. You can find the uh, final thing, and then you can just apply the limits after you get the final integration. Okay, so substitution, I don't think we have time to cover it. So what I'll do is I'll take a doubt session this week for the remaining doubt session. So we have these two logarithmic, which is basically rationalizing a polynomial function, and a substitution method, which are very important. So I'll do that. I'll take doubts for the problem set on Thursday. All right, so maybe Monday or Tuesday we can schedule it. What works for you guys? Since you guys are the regulars who attend it, other people are more like visiting students. So, what works for the three of you? Will Tuesday work? Tuesday, let's say 6 o'clock, 6 p.m.
Yes, sir. Any of the one will work.
All right, fine. So tentatively, let's put it on Tuesday since none of you are objecting to it. I'll put it on the group and see if it works for everyone. We'll take a doubt session on Tuesday. So first half an hour, I'll do this, complete this up. Shouldn't take half an hour, more than half an hour. And after that, we'll move to taking the doubts. All right. So let's end this for today.
Excuse me, sir.
Yeah.
Sir, may you please provide the written solutions for first 5 problems of uncertainty?
Okay, fine. I'll do that by this Sunday.
Okay, sir. Thank you.
All right. See you tomorrow. So tomorrow, what time? 4 o'clock. So we have the lecture at 4 o'clock. So I'll see you guys tomorrow. Bye.